Hi, I'm Megan.
I'm Pearl.
I'm Toby.
I'm Joshua.
And we'll be presenting on the first and second derivative test.
So the first derivative test. So the first step is of course to take the derivative. In this case, we have f of x equals to 6x minus x squared. So after you take the derivative, you get 6 minus 2x, right? And the second step is to find the critical numbers. So to find the critical numbers, you make the derivative you got equal to 0 or undefined. In this case, we make it equal to 0. So 6 minus 2x equals 0, you solve for x and x equals 3. But remember, if the critical number makes the original function undefined, it is no longer a critical number. And now the third step. Plug into f of x the numbers on the left and right sides of the critical number. So we have 3 here, so you can plug in 2 on the left side and 4 on the right side. So when you plug in 2, you get 2, a positive number. And then when you plug in 4, you get negative 2, a negative number. So if it's positive, it's increasing, and if it's negative, it's decreasing, right? Positive, increasing, negative, decreasing. And then if you want to find the maximum and minimum, if it's from increasing to decreasing, in this case is increasing to decreasing, it's a maximum. But if it's decreasing and increasing, it's a minimum.
So here we have another log example. And next we want to take the derivative of it. So you'll do is just expand x plus 4 squared, and then you put in 3 and distribute it throughout the whole quadratic equation. After that, you'll use your quotient rule for your logs, and you'll take the derivative of the log function for each to make it equal this. And to find the critical numbers, you set this equation to equal 0 or undefined, which is -4, 0, -7.9, and -1.5. But because -4 makes it the original equation undefined, -4 cannot be a critical number. So next we find the intervals between each critical number. So we take a value in between each interval, and eventually you conclude whether it's increasing or decreasing. So after we get in the conclusion, the relative maximum is -7.9 and at 0 too. And the relative minimum is also at x equals -4.
So a summary of the second derivative test. The graph of the second derivative of f shows the concavity of f. And the purpose of the second derivative test is to find the relative extrema and the points of inflection of the graph of f. And if there's a positive second derivative, then that means that the graph of f is concave upward. And if there's a negative second derivative, then it means the graph of f is concave downward. So onto the second derivative test. The actual test is to find, let f be a function where the first derivative of f equals 0 and the second derivative of f exists on an open interval containing c. So if the second derivative is greater than 0, so if it's positive, then f has a relative minimum at c. And if the second derivative is negative, then f has a relative maximum at c. And it's really important to remember that if the second derivative is equal to 0, then the second derivative test fails. And then we have to move on to apply the first derivative test, which we already explained. Because f may still have a relative maximum or relative minimum, or neither. But yeah, in order to find out, you have to use the first derivative test.
So this problem is like a basic problem where you would use the second derivative test. So your first step is to simplify the problem, and your second step is to take the first derivative, and then you would take the second derivative of the function, and then you would set the second derivative equal to 0 and solve for x in order to find the critical numbers. So for this problem, the critical numbers are plus or minus 2. So you would use the critical numbers in order to split the interval into separate sections. So for this problem, you have an open interval, meaning that it goes from -infinity to positive infinity. So you would use the critical numbers to divide it into -infinity, -2, -2 to 2, and 2 to infinity. And then after you would find test intervals which would fit into this interval. So for example, for this interval we have -infinity to -2, so we would have a test value at x equals -3. So what you would do is that you would take the test value and plug it back into the second derivative in order to determine whether the function is concave upward or concave downward. So for this one, the second derivative of -3, when you plug it in, is greater than 0, meaning that it concaves upward. So then here we have the it concaves upward, then downward, then back upward, meaning that the direction changes twice. So that means that there are 2 points of inflection. In order to solve for points of inflection, you would take the critical numbers and plug it into the original function. So for example, we have positive 2, so you plug the positive 2 into the original function and solve in order to find the y-coordinate. So for this one, we have 2, 3/2, and you would do the same for the second critical number. So this is an example of a more challenging problem using the second derivative test. So here we have f equals x to the 4th power. So you would take the first derivative, so it would be 4x to the 3rd, and then you would take the second derivative, which would be 12x squared. So you would set the 12x squared equal to 0, and then you would solve for x, which is the critical number. So the critical number for this problem is 0.
So because x equals 0 is a critical point, then the second derivative test fails. And then you have to use the first derivative test to find out whether or not there's a relative extrema at x equals 0. So you plug in x values, both less than 0 and greater than 0. So we used x equals -1 and x equals 1. And then you plug the x values into the first derivative, which is 4x cubed. So for x equals -1, the first derivative is -4, and for x equals 1, the first derivative is 4. So the conclusion is that when x equals -1, the function f is decreasing on the interval -infinity to 0 because the first derivative is negative. And for when x equals 1, our conclusion is that the graph of f is increasing on the interval 0 to positive infinity because the first derivative is positive. And so x equals 0 is a relative minimum of f because at x equals 0, the function changes from decreasing to increasing as shown through this sample graph of f. So it's decreasing from the open interval -infinity to 0, and it's increasing on the open interval 0 to positive infinity. And the minimum is at x equals 0.
Thank you for watching.